All right, the last section, there's really no math, even though they do show you some equations in here. Again, you might need one or two of these for your homework, but I don't want you to do any math for the exam or anything. This is more just understanding what colligative properties are. Okay, and basically the properties of a solution that depend only on the number of particles, not on the concentration, I'm sorry, not on the type of particles, like hydrogen bonding, polarity or anything like that. It's just having extra particles. And this is kind of going to explain why we put salt down on the ground when it snows outside. All right, that's something that we deal with. Also, when we put salt in our water to when we want to boil water and make it hotter. There's a few things going on there. It's not just the colligative properties, but it's also interaction. So there's kind of both things, but we will talk about what the colligative properties. All right, now here's this equation that they always use for colligative properties, which is it's pretty simple, but again, it's not something you need to know on the exam. I just care more about that you understand what freezing point depression is. This is based on the salt, is putting salt on ice when it snows outside. Okay, when a substance such as salt is dissolved in water, the freezing point of water is lowered. Okay, so we know that the freezing point of water is 0. Okay, well, when you put a salt in, depending on the salt, it can change. It can change the freezing point by a certain amount. All right, I believe magnesium chloride, you've heard it, mag chloride, those trucks that come around, mag chloride, drops, I believe, the freezing point of water somewhere between 10 to 20 degrees Celsius, which is kind of a drastic change. It all depends on the concentration, okay? It depends on how many particles you have. So by adding magnesium chloride, you drop the melting point or the freezing point of water quite a bit. So that means, let's say you put mag chloride on the water, it now has to be, let's say, 20 degrees colder than the freezing point of water for it to freeze. So that means it has to be negative 20 degrees outside um, uh, in order to freeze water. Okay, so that's kind of what this is all about. And here's an equation to actually figure out how far it's lowered. All right, and what's the reasoning behind it? There's a lot of different ones. One is that water, when things freeze, they are very ordered. Okay, the water molecules have to be very ordered in order for it to freeze, and they all pack on top of each other in a crystalline fashion. Well, if you have impurities, okay, trapped inside of the water, such as salt molecules, the water can't form this crystal lattice. It can't kind of all pack on top of each other in a nice fashion. So it takes so because of it, it has a little bit higher energy. It can't freeze. It can't like form a crystal. Eventually, you take enough energy out of it that all the particles stop moving or slow down so much that it actually freezes. Okay, but that's kind of one of the theories. Also, the other theory is that you're forming this ionic hydrogen bonding. And then there's another one, there's like an energy one that just talks about how much energy is incorporated inside of it. All right, we're really not going to go into like way too much of it, but that's kind of the real quick and dirty way of explaining it, is that you all disrupt its crystalline lattice so it can't pack as nicely, and it's having a hard time in freezing. Okay, so this equation, just to kind of show you, it's a change in your temperature. So it's the number of degrees of which the freezing point is lowered. So for mag chloride, 10 degrees, 20 degrees. All right, the Kf is a constant. Okay, so it's a freezing point depressant constant of water, which is 1.86. And then the M is the molality. So we're talking molality. This is kind of where the molality is used. So it's a certain concentration. All right, so ethylene glycol, all right, is a common automobile antifreeze. If the water, it is water soluble and fairly non-volatile, okay, great. Calculate the freezing point of a solution containing 11.08 moles of ethylene glycol in 2,079 grams of water. All right, well, you need to know the molality. So what do? You have your moles and you have your kilograms of water. You figure out the molality and you plug it in there. So your molality is 5.321, and you get about a 10-degree change. All right. So if you take antifreeze and you put it in water, it means that that it won't freeze until it's 10 degrees lower than the freezing point of water. Okay. It's actually affected the freezing point of water. Okay. So that's why we use antifreeze instead of our engines. Okay. Here's the opposite effect, is the boiling point elevation. Okay. You can put something in water and actually increase the boiling point. Like we put salt in water because because water boils at 95 degrees, but we want it to boil at 100 degrees. So you put a solid, or you put like something inside of it in order to change it. Okay. Same thing. You have a molality. You have your K for boiling water, which is 0.512. So your constant has changed. All right, so glycerol is a common ingredient in pharmaceutical and personal care products. Calculate the boiling point of a solution containing 7.75 moles of glycerol in 1,895 grams of water. Same thing, figure out the molality, plug it in, and you have a difference of 2 degrees. So glycerol will change water by 2 degrees. Really nothing too amazing. Okay, so you know, technically, if you wanted to calculate, so for example, water boils at 95. Let's say you wanted to raise the temperature 5 degrees and you're boiling pasta. You can technically, if you would like to, calculate how much salt you would need to add to raise it by 5 degrees. Okay? Um, you know, how do you do that? Well, remember your molality, which is moles of your solute divided by your kilograms of your solvent. All right, and you want to change it by 5 degrees Celsius. So if you're using a liter of your solvent, all right, that's about 1,000 grams. All right, so whatever you're, okay. So if you have a liter, so the density of water is 1 gram per milliliter. Okay, so you can figure out if you have a liter. Okay, if you have a liter, then you have, so 1 kilogram is equal to a liter of solvent. Okay, so this is 1 kilogram. You have 5 degrees. And then you have your K of water, which was 0.512. You can figure out how many moles of salt that you want to put in there, and then in turn you can figure out how many grams of salt it is. Okay, we'll let you do that on your own, but that's kind of an interesting equation. All right, and then the last one is osmotic pressure. So osmosis, everyone's kind of heard osmosis. It would be great to, you know, everyone always says the classic joke is, I wish I can take my book and put it up to my head and by osmosis learn all the information. Okay, because things go from a highly concentrated to a lower concentrated amount. Okay, so this basically, I'll just kind of show you a problem. You have a semi permeable membrane. All right, and on one side I have just pure water. This is just pure water. On this side I have a very concentrated solution. All right, and only water is able to travel through here. Okay, and basically what happens is things want to be equal on both sides. So water is going to be, all the water, since this is much more concentrated, water is going to be flowing towards the more higher concentrated area. So if you read this, in an aqueous solution and pure water are separated by a semi-permeable membrane, one through which water molecules can pass, but solute particles cannot. Water molecules will move through the membrane from the pure water side to the solution side. This is called osmosis. The pressure necessary to stop the flow of water across the membrane is known as osmotic pressure of the solution. The greater the solution's concentration, the higher the osmotic pressure. Okay, so basically the pressure incorporated in having the actual water flow through here is osmotic pressure, but that's basically what osmosis is. All right, so I believe that is it for this chapter. Oh, here's actually an example of a red blood cell where you have this osmotic pressure or osmosis. I believe the one on the right is, so this is a normal cell. All right, this is a cell that has a lot of water inside of it. All right, it got very concentrated, and I believe this is a cell of a patient that has sickle cell anemia, where you have this irregular shape in blood. All right, it's kind of showing you how osmosis is related to that. Okay, so that's it. Any questions we will talk about in class.